Learning Target 13 says I can translate between sigma notation and an expanded form sum. So just as a reminder, this is an example of sigma notation. It's a way of writing out a sum in this sort of concise way. So rather than writing 1 plus 4 plus 16 plus and so on, and giving a whole long list of numbers that you're summing, instead of writing it out like that, this is sort of a concise way of describing the sum. It's sort of like writing an equation for a function. It's a concise way of describing the sum rather than saying every single term in the sum and actually writing it out. Expanded form sum means when you actually do write it out as a sum, 1 plus 2 plus 4 plus 8 and so on. You actually write it out as an expanded form sum. So the idea with sigma notation is that there's going to be a function on the inside that describes each of the terms in the sum. And then at the bottom and the top of the little sigma symbol, it's going to tell you the first k value you should plug into the inside formula, and the last k value you should plug into the inside formula, and you sort of go from 0 up to 5, plugging in those k values into this formula, and those are the values that you are summing up. So let's see an example. Number 1 asks you to write this sum as an expanded form sum. So what that means is translate from this sigma notation into expanded form. So what we're going to do is we're going to take each of the k values indicated here, plug them into our formula on the inside, and each k value we plug in will give us a term in the sum. So first we're going to plug in k equals 0. So we get 4 times 2 to the 0 on the inside. So that's going to be the first term of our sum. Next, we're going to plug in the next k value. We started at 0. We're going to now go up to 1. So 4 times 2 to the 1. Then we'll go to the next possible k value, which is 2. Plug in 4 times 2 squared. Then we'll plug in the next k value, which is 3. So 4 times 2 to the 3. Again, all I'm doing is I'm plugging in k values from 0 up to 5, and I'm plugging those k values in for k in our inside function formula. So our next k value is 4, so our next term is 4 times 2 to the 4th. And then when we plug in k equals 5, we get 4 times 2 to the 5th. And we can tell where to stop based on whatever the number at the top of the sigma is. That tells you what is the last k value you should plug in. So we started at k equals 0, and then we plugged in all the possible values for k up to k equals 5. And we could tell that we needed to stop at k equals 5 because that's the number on the top of the sigma. Now we should simplify a bit. I should have actually written in the directions as a simplified expanded form sum. So what I mean by that would be that you actually simplify each of these terms and write them as like a single number. Like, is this equal to 8? Is it equal to 72? What do each of these pieces, what number are they equal to? So to start, we have 4 times 2 to the 0. 2 to the 0 is just 1. Next, we have 4 times 2 to the 1st. 2 to the 1st power is just 2. 4 times 2 squared. 2 squared is 4. So all I'm going to do is I'm going to first deal with the exponents, because I know that's what I'm supposed to do in order of operations. And I'll just sort of go through within each of these terms and figure out what the 2 to the power is equal to. So then I'm still left within each term with a product, and once again, I don't want to leave this term as 4 times 1, I want to actually write it out as 4. So we can find each of these individual products. So 4 times 1 is 4, 4 times 2 is 8, 4 times 4 is 16, and so on. And this is our expanded form sum. So if it asks you to write it as an expanded form sum and doesn't ask you to actually find the sum, you just want to leave it in this format where you translate the sigma notation into a sum of numbers written out like this. So this problem asks us to actually write the sum in sigma notation. So we know that in sigma notation, we're going to have our sigma symbol. We know on the inside we're supposed to have a function formula that represents all the terms in the sum. And then we know that on the bottom and on the top we're supposed to write down what's the k value that we would plug into the inside function formula to give us the first term. And then up at the top we're going to write what's the k value that we need to end at, so that when you plug that k value into the function formula you actually get out the last term. So the first thing that we have to do is we need to think about a function formula for this sum. So let's first think about whether this is an arithmetic or a geometric sum. So as we go from term to term, it looks like we're adding 3 each time. So if we're adding the same number each time, then we know that our sum is going to be arithmetic. And to write a formula for an arithmetic sum, we know that it's going to have some sort of a linear function formula. So it's going to be some number multiplied by k plus some other number. This is sort of like y equals mx plus b form. In this case, the number that goes in front of our variable k is going to be the number that we go up by each time. So this will be a 3. If you were going down by 3 each time, you'd put a negative 3 in front of the k. And the number that goes out here is what our very first term in our sum is. So that'll be a negative 6. So a general formula for each term in this sum is going to be 3k minus 6. So that's what's going to go on the inside of our sigma notation. So now the harder thing to figure out is what are the k values that I should start on and end at. So we know that at the bottom, that's going to be the k value that we would plug into our function formula to get the first term. The k value that goes up at the top is going to be the k value that we would plug in to get the last term. So let's think about what k value we need to plug in to get negative 6. So one way of thinking about that is to say, well, we know that the inside function formula, we're supposed to plug some k into that, and we're supposed to get out negative 6. So you can think about that sort of like an equation that you know that 3k minus 6 needs to equal negative 6 for some value of k. So that's just an equation that we can solve for k. So we're going to do that by first adding 6 to both sides. So that gives us 3k equals 0. And then to solve for k, we're just going to divide both sides by 3, and we just get k equals 0. So our very first k value is going to be 0. And if we plug in k equals 0 to the inside function formula, we should get out our first term. Now if we plug in k equals 1, we should get our next term. If we plug in k equals 2, we should get our next term. However, we don't really know, we don't know how many terms are in the sum, so we don't know what our very last k value is going to be. So we now need to solve for what k value would give us that last term. So once again, we're going to solve an equation. We're going to write 3k minus 6 is equal to 18, and we're going to find the value of k that we could actually plug in that would make 3k minus 6 be equal to 16. So to solve this equation for k, we're trying to get k by itself. So the first thing we'll do is we'll add 6 to both sides. On the left-hand side, we're left with 3k. And on the right-hand side, we get 18 plus 6, which is 24. So then we can divide both sides by 3. And we get k equals 8. So if we were to plug in 8 into our function formula here, we would get out 18. So we know that that's the last k value we want to plug in that will give us our very last term. So let's just quickly review what we did here. We first figured out that it was arithmetic. The formula for an arithmetic will be some number times k plus some other number. The number in front of the k will be the number you go up by each time. The number that we're adding on is going to be our very first term. That function formula goes on the inside of the sigma, and then we have to solve for the k values that would give us our first term and our last term. Those k values go at the bottom and the top of the sigma. So here's another example to try where I give you an expanded form sum and you need to write the sum in sigma notation. So once again, we know that we're going to have our sigma symbol. On the inside of the sigma, we want to write a function formula that represents the terms in the sum. At the bottom of the sigma, we'll put the k value that we would plug into our formula to get the first term. At the top, we're going to put the k value that we would plug into our formula to get the last term. So the first thing that we have to do is come up with a formula that represents the terms in our sum. So let's first think about whether this is arithmetic or geometric. In this case, as we go from term to term, it seems like we're multiplying by 3 each time. So since we're multiplying by the same number each time, we know that our sum is going to be geometric. So that helps us to figure out what kind of a function formula we're going to have. For a geometric sum, the function formula that will represent each term is going to be something that is exponential. So it's going to be something of the form a times b to the k, where the b value is the number we multiply by each time, and the a value is just going to be our very first term. So the formula for our geometric sum will just be 5 times 3 to the k. And that formula is what goes on the inside of our sigma notation, like this. So the next thing that we have to do is we need to figure out what is going to go on the bottom and the top of our sigma symbol. And once again, on the bottom we put in the k value so that when we plug it into this formula, we get our first term. Up at the top here, we're going to put in the k value so that when you plug it into the formula, you get your last term. So over to the side here, I'm going to say, okay, so for what value of k is this formula equal to my first term, 5? So now I have an equation that I can just solve for k. So to solve for k, I'm going to divide both sides by 5. So I get 3 to the k is equal to 1. Now, there are methods of solving equations like this that it involves logs, which we'll learn about at the end of the year. But for now, you just sort of have to guess and check to find a value of k that makes this equation true. Any number raised to the 0 power will give you out 1. So if you have 3 to the k equals 1, k equals 0 would satisfy this equation. So that's our very first k value, and that's what's going to go on the bottom of the sigma. So now let's try to figure out what should go on the top of our sigma. So once again, I'm going to take my formula on the inside, and I'm going to set it equal to the last term in the sum, and I'm going to try to figure out what value of k would make this equation true. So the first thing that I'm going to do is I'm going to divide both sides by 5. So then we need to divide 45 divided by 5, and we get 729. Now, once again, there is a way of solving for k. It involves logs, which we'll learn later on in the year. For now, you just sort of have to guess and check, like play around on your calculator and do like 3 to different powers until you end up getting 729. So you might guess, oh, maybe it's 5, and see is that above or below 729. If it's below, then you want to keep going up in your k value. You just sort of have to guess and check until you figure out a value of k, so that 3 raised to that power would give you 729. In this case, if we did 3 to the 6th power, we would get 729. So that means that our k value that we could plug into our formula to get our last term would be 6. So that's the very last k value that we're going to plug in. So 6 goes at the top of the sigma. So let's just once again review the steps to this procedure. We have a sum that we want to put into an expanded form sum. We first had to find an equation that represented that sum. After we found the equation that goes on the inside, we figure out what k value do we plug into the equation to give us 5, that was this work over here, and then what k value would we have to plug into the equation to get the last term, that was this work over here. The first k value goes on the bottom, and the last k value goes on the top.